Hello, my name is Andrew, and today I'm going to be doing a presentation on distributed attack detection and secure estimation of networked cyber-physical systems against false data injection attacks and jamming attacks. This paper was written by Dr. Yanping Wang and Xiaohua Ge. The focus of the paper is distributed attack detection and secure estimation of a system under a simultaneous physical and cyber attack. The type of attacks that are going to be observed today are going to be false data injection attacks and denial of service attacks, or could be commonly known as jamming attacks. The system type that's under observation is a cyber physical system, which we'll go ahead and explain a little bit later in the presentation. And the concern is inadequate attack detection by control systems and inaccurate distributed secure estimation problems that stem from concurrent attacks on a CPS over a wireless sensory network. The major industries that are impacted are going to be aerospace, civil infrastructure, power grid networks, water and gas distributed networks, and transportation networks. Some of the key terms that we're going to use in this presentation are going to be a cyber physical system. This is actually going to be an aggregation of different systems that include computational devices, networking devices, and physical processes that go into protecting a cyber network. Denial of service or a jamming attack is going to be an attack that eliminates legitimate access to systems, services, or applications, or it could also be one that disrupts the reception of legitimate network traffic. The false data injection attack is going to be an attack in which an adversary successfully receives network traffic, modifies it in a way that falsifies the physical system's state, and this is done through sensory data, control commands, and then the adversary will actually introduce errors, fake information, or faulty data into the system. The networks that we're going to be looking at are going to be the wireless sensory network. This is a geographically spaced sensory node network that is in charge of regathering, transmitting, and communicating amongst the other sensory nodes on the network current real-time environmental data. The estimator network is the secondary network in this communication network that receives the information from the sensors. It calculates the current state of different parts of the environment based on sensory node location and relays this real-time environmental data to a control center that monitors the overall network health. The last one is going to be a continuous stirred tank reactor, and this is an open system where material is free to enter and exit the system that operate on a steady state basis where the conditions in the reactor don't change over time. The motivation of this paper is that there are actually few studies that focus on not just attack detection, but also secure estimation for CPSs over a wireless sensory network. But also, there aren't very many that study the effects of these two areas when there's a simultaneous physical and cyber attack. Some of the contributors to the motivation of this paper is that geographically distributed observation and sensory nodes pose a significant problem in data gathering, especially in the midst of a malicious attack. Second is going to be a majority of the existing works focus on secure estimation of CPSs are limited to a single node, this making it inapplicable to a wireless sensory network that has multiple nodes spread across a large geographical area. The third one is going to be existing literature mainly focuses on a single type of attack, and few consider simultaneous attacks when they're occurring on a CPS. Some of the contributions that this paper or research seeks to provide is will provide sensory nodes with a refined compensation-based measurement output model. And this is because each estimator will actually admit and utilize corrupted sensory data from itself and from its neighbors when experience a jammed transmission attack. The second is going to be a resilient attacks estimator, which will be delicately constructed to deal with simultaneous effects of an FDI attack, jamming attacks, as well as process and measurement noises that occur in the environment during these types of attacks. This is going to be done through a two-step attack detection mechanism, which will return and recognize and alarm during an FDI attack. A secure estimation problem under attack will be mapped to an infinite estimation problem to increase estimation system resiliency. And then the criteria for analyzing secure estimation performance and designing desired estimators will be derived to guarantee the feasibility of the proposed distributed attack detection and secure estimation problem. And this is because analytical and numerical investigation for verification, to at which point the resultant estimation error system will converge in the presence of simultaneous attacks, as well as process and management noises. The wireless sensory network that we're going to be taking a look at is going to be made up of two different types of networks. The first is going to be a sensory network, which is in charge of actually taking in environmental data and broadcasting it to our estimating network. Now, the estimator network is actually going to be estimation nodes that receive data from different geographically dispersed sensory nodes, and it will make calculations about the current state of the environment, and this will go ahead and forward this information over to a control system. To help with secure estimation, the ideal measurement output model was created. The ideal measurement output model was created because data transmission or measurements that are received by estimators are actually explicitly assumed to be ideal or true. This is a problem because during a denial of service attack, transmissions that are coming from legitimate sources, such as the sensory nodes, are actually completely dropped or only partially received by the estimator nodes. This allows for any data transmitted by the attacker that is received by the estimator nodes to be assumed as truthful information, which can definitely disrupt the secure estimation of the actual health of the system. And so again, this ideal measurement model is used to compensate for false data that's received, as well as measurement noises that are received by the system over the wireless channels. Using the equation below, again, a secure estimation will be created by taking a measurement that is generated from the attack, as well as combining that with a compensated measurement due to an attack by false data injection. And then finally, a measurement of noise experienced by the wireless channels will be added to create a secure estimation. Actual detection of a false data injection attack will actually come in by way of a two-part process. First, we're going to generate a residual signal on each estimator, and then we're going to analyze the signal that's generated from the false data injection attack against a residual signal threshold. And again, we can look at this equation down at the bottom. Again, this will define what is currently happening over the network in terms of signals being transmitted from sensory and or measurement noises, or even signal received by attackers, and it will determine its place against a threshold that's previously set by the system, and depending on whether that threshold is exceeded, it will actually go ahead and alarm the system of a false data injection attack that is occurring. If it falls below that threshold or is equal to the threshold, then it will go ahead and not signal an FDI attack. For the experiment, we're going to use a continuous stirred reactor tank, which is going to run for 300 seconds. During that 300 seconds, measurements of temperatures are going to be taken by sensory nodes that are set up geographically throughout the tank and transmitted to the wireless estimators, which are going to be stationed in a processing center, and the transmissions are going to be received over wireless transmission channels. Figure 6 demonstrates the evolution of the state estimation errors throughout the 300-second experiment. The estimations eventually return to zero as time passes, and this verifies a proper estimation of the state of the reactor throughout the experiment. Using figure 7 below, it actually shows residual response with and without both process and measurement noise to the above false data injection attack signal from all four sensors. After the 300-second experiment, we used figure 8 to actually show a graphical representation of every estimation that was generated by the estimator network and individual estimators themselves. So looking at the graphs on the left, we'll actually see that the blue line represents the residual evaluation created by the ideal measurement output model. And that's again represented by the blue line, and the threshold is the pink line down at the bottom of each graph. And then when you crossing the threshold, when cross-referenced with the confirmed estimations, initiated alarms which actually successfully signified or signaled an FDI attack occurring. To conclude, false data injection attack detection was handled by a two-step attack detection mechanism, which has been established through which the occurrence of an FDI attack can be detected and successfully alarmed. To tackle secure estimation due to a jamming attack, a refined measurement output model based on compensated measurements has been proposed, and resilient estimators have also been properly constructed. In the closing arguments, the criteria for estimation performance analysis and estimator design has been derived to guarantee the feasibility of the problem, and the effects and application of the results were authenticated through the use of the networked continuous stirred tank reactor during our 300-second experiment.